In this video, we'll explore how to evaluate the quality of a Bayesian regression model. Consider an example. Suppose we wish to model the daily number of users for a bike share service by the temperature on that day. The results of our Bayesian posterior analysis of the relationship are displayed here. Each line represents a posterior plausible description of the regression model between ridership and temperature. We learn from these that there's almost certainly a positive association. That is, the warmer the weather, the more riders we tend to observe. Yet, before we go applying or reporting this model, it's important to ask some follow-up questions. For example, would you eat a foraged mushroom without asking about its safety? You shouldn't. Would you take a prescription drug without first learning about its effectiveness and side effects? You shouldn't. It's similarly risky to use or report a model without asking how good it is or evaluating its quality. To this end, there are 3 important questions to ask in a model evaluation. Is the model fair? How wrong is the model? And how accurate are the posterior predictions? Consider the first question. Is the model fair? The answer to this question is context dependent and not cut and dry. To this end, we can examine different elements of our analysis. First, consider the data collection process. It's important to understand how, by whom, and for what purpose the data were collected. Similarly, we need to understand who was included in or excluded from this process. Beyond data collection, we also need to understand the implications of our work. How might the results of the analysis or the data collection itself impact individuals and/or society? What might be the benefits or harms associated with our analysis? Finally, we must carefully examine the potential biases baked into our work. That is, what biases might be introduced by the type of data we're using, our analysis of this data, or even our own perspectives and biases. In our bike share analysis, our model is likely fair. The data were collected by the Capital Bike Share Company in order to better anticipate and prepare for daily operations, and anonymized before they got into our hands. Further, the implications of this analysis are unlikely to harm any customers or have unethical consequences. That said, we still might want to dig in further. For example, we might ask whether the privacy of customers was preserved in the data collection process. Consider the next model evaluation question. How wrong is the model? As you've likely learned, all models are wrong, but some models are useful. By this, we just mean that models are merely hypothetical representations of more messy realities. Even so, when done well, models can provide some insight into that messy reality. Consider an example. The model on the left is good. It appropriately assumes a quadratic relationship between our variables y and x. The model on the right provides an example of a wrong model. It inappropriately assumes that the relationship between y and x is linear. The more and more complicated our models get, we won't be able to rely on simple graphics like these. Instead, we can conduct a posterior predictive check to assess the quality of our model structure. There are a few steps behind this process. First, we can check out our Markov chain simulation output. Suppose that we run our simulation for 20,000 collective steps or iterations. Each of these steps, or each row in our chain output here, then presents a posterior plausible set of regression parameter values. Or we can think of these as 20,000 possible worlds for the relationship between ridership and temperature. Once we have our chain results in place, we can then simulate a sample of response values y from each of, say, just 50 of the 20,000 parameter sets. For example, consider the first posterior plausible set of parameters highlighted here. Then from each observed temperature in our sample dataset, we can simulate a possible ridership outcome under this scenario. Specifically, we can simulate ridership values from a normal model, where the mean is defined by negative 2,339.928 plus 84.37713 times temperature. And the standard deviation is defined by the sigma parameter, 1,289.935. Finally, we can compare the simulated sets of y values to the actual sample of y values. Here, we observe that our first posterior plausible set produced a sample of ridership data represented by the light blue line. And this density curve in light blue is barely visible. This simulated data has different features than the observed ridership data, represented by the dark blue line. However, we don't want to evaluate how wrong our model is using just one of 20,000 posterior plausible parameter sets. Instead, suppose we repeated this process 50 times. That is, we simulated ridership data from each of 50 different posterior plausible parameter sets. This collection provides us with a better sense of how wrong or not wrong our model is. Repeating this process for all 20,000 parameter sets would be unnecessary and computationally expensive. Here, notice that our regression model of ridership seems to adequately capture the typical ridership around here, as well as the range in ridership. However, it does not pick up on the apparent bimodality in the observed ridership. This would be something to keep in mind when improving our model. Finally, consider our third model evaluation question. How accurate are the posterior predictions? For example, consider the posterior predictive model of ridership for an 80-degree day. It indicates that ridership will most likely be around 4,400 rides, but might range anywhere between, say, 2,000 and 8,000 rides. Next, suppose that we end up observing 6,000 rides on an 80-degree day. This observation is marked by the vertical line. So how did we do? That is, how does our posterior predictive model of ridership compare to this observed outcome? As a point of comparison, suppose we had a second model that produced the posterior predictive model here. Comparatively, notice that our first model provided the better prediction. The posterior predictive model here seems more consistent with the 6,000 rides than the model here. To formalize and communicate this observation, we can obtain 4 different metrics, or 3 kinds of metrics. First, we can ask how far the observed response value y is from its posterior predictive mean, that is, from the typical posterior prediction. In the case of Model 1, the posterior predictive model has a mean of 4,400 rides. Thus, our observed 6,000 rides outcome is 1,600 rides above this posterior mean prediction. In fact, the result is the same for Model 2. Just as with Model 1, the posterior predictive model here is centered around 4,400 rides. Thus, our observed 6,000 rides outcome is 1,600 rides above this posterior mean prediction. This result reveals a flaw in just focusing on the distance, or the raw distance, between an observed outcome and its posterior predictive mean. Mainly, it ignores the scale of the posterior model, thus can produce misleading results. Thus, as a follow-up, we can ask not just how far an observed outcome is from its posterior predictive mean, but how many standard deviations it falls from the mean. This provides a more standardized metric for comparison. For example, the posterior predictive model for Model 1 has a mean of 4,400 rides with a standard deviation of 1,060 rides. Thus, subtracting the mean from our observed 6,000 rides and then dividing by the standard deviation reveals that our observed ridership is 1.5 standard deviations above its mean prediction. In contrast, the posterior predictive model for Model 2 also has a mean of 4,400 rides, but a much smaller standard deviation of 350 rides. Thus, in this case, the observed 6,000 rides falls a whopping 4.6 standard deviations above the mean. In the context of a symmetric posterior predictive model like we have here, 4.6 standard deviations from the mean lands you far into the tails of the model. Beyond comparisons of our observed outcome to its posterior predictive mean, we can consider the coverage of our posterior predictive model. For example, we can simply ask whether our observed y value falls within its 95% posterior prediction interval. These intervals are shaded blue for the posterior predictive models at right. Notice that the observed 6,000 rides does fall within the 95% prediction interval for Model 1, but outside this interval for Model 2. Similarly, we can ask whether our observed y value falls within its 50% prediction interval. For both models, the answer is no. Reflecting on our results for Model 1, we saw that the observed 6,000 ridership outcome fell inside the 95% posterior prediction interval, but outside the 50% interval. This just means that our model considered 6,000 rides to be within the realm of possibility, but it didn't consider it to be one of the more plausible outcomes. Now, we've evaluated the posterior prediction quality for just one data point. To better understand the overall quality of our model predictions, we can ask these same questions for every data point in our sample. At left is a scatter plot of ridership versus temperature for all 500 data points in our sample. For clarity, the right plot shows just a subset of these data points. Notice that for each observed data point, marked by the dark blue dots, there's corresponding information about the posterior predictive model for ridership, represented by the lighter blue color. For example, the light blue dots represent the posterior median predictions of ridership at that given temperature. Further, the narrower, longer light blue lines, like this one here, represent the 95% prediction intervals for ridership. And the wider, shorter light blue lines represent 50% prediction intervals. Thus, this plot provides a visual tool to assess the distance between our observed ridership values and their posterior predictive medians, as well as the coverage of the posterior prediction models. We can also numerically summarize this information using the prediction summary function in the Bayes rules package. Consider the reported MAE value. In general, the MAE, or median absolute error, measures the typical distance between the observed y values and their posterior predictive means. Specifically, we calculate the absolute differences between each y value and its predictive mean, and then calculate the median of these differences. Ideally, the observed y values will be close to their predictive means. Thus, we want MAE to be small in the context of what we're measuring. In our example, the MAE is 993.0029. That is, our posterior mean predictions tend to be off by 993 rides. Whether this is a big or small number depends upon the context. In this example, the observed ridership only ranges from roughly 0 rides down here to roughly 6,500 rides up here. Thus, a prediction error near 1,000 riders on this scale seems pretty big. Next, the scaled MAE takes into account the scale or spread of the posterior predictive models. Specifically, it measures the typical number of standard deviations that the observed y values fall from their posterior means. In general, we also want this metric to be small. In our example, the scaled MAE is 0.77. That is, the observed ridership values typically fall within 1 standard deviation of their posterior mean predictions. Finally, consider the within 50 and within 95 statistics. The within 50 statistic measures the percentage of observed y values that fall within their 50% posterior prediction intervals. We expect this to be around 50%, and in general want it to be high. This would mean that our observed y values fall close to the center of their posterior predictive models. In our example, 43.5% of our observed ridership values fall within their 50% posterior prediction intervals. Or 43% of these blue dots fall within the corresponding narrow blue lines. Now, this isn't terrible, but it does suggest that observed ridership outcomes might fall more into the tails of their posterior predictive models than at the center of these models. Finally, 96.8% of our observed ridership values fall within their 95% posterior prediction intervals. That is, almost all of these dark blue dots fall within these wider light blue bars. That is, our model is pretty good at covering or anticipating ridership. Stepping back from the details, we've explored how to address three important questions for every Bayesian model. Is it fair? How wrong is it? And how accurate are its predictions?